Question number 13. Here we have been referred to a conductor, and we know that resultant field at point C should be 0. The resultant field at C has got contributions from two sources, one external charge Q and the other appearing on the outer surface of the shell. So, the field created by external charges at point C is being cancelled off by charges appearing on outer surface. We have to just calculate the field of charge Q, which is 1 upon 4 pi epsilon naught Q upon 3a whole square. This is field created by Q, and this field acts in positive x-axis direction, that means towards right, which implies the field created by charges appearing on outer surface must be opposite to this field. That means the required field vector is negative of this vector, 4 pi epsilon naught Q upon 3 whole square minus I cap. That means one of the option A is correct. Now check for the option B. We say that what is potential before closing switch. Before closing switch, potential at point C has got contribution from minus 3Q and Q and induced charges. But since additional induced charges that appear make zero resultant potential here, then net potential at this point will be minus 1 upon 4 pi epsilon naught 3Q upon A, which is due to this charge, and potential of this charge, which is 1 upon 4 pi epsilon naught Q upon 3A, which makes option B correct. Lastly, we come to option C. After closing switch, charge of the shell is this. So when switch is closed, the potential of this shell becomes 0. Now we assume, suppose an induced charge Qi appears on it after closing the switch. Now calculate what is potential at the center, which is 1 upon 4 pi epsilon naught Qi upon A due to induced charges appearing on this, and the other is potential of the outside charge, which should be 0. That means the induced charge becomes minus Q upon 3. That makes option C correct. Then we check option D. After closing P, charge of the shell is 0. As we see, net charge is minus Q by 3. So finally, our options are correct options are A, B, and C. So next, question number 14. In this question, first of all, we have to find out what is charge appearing on the inner shell after grounding this shell. So we assume the charge Qi appears on it. Net potential of this shell must be 0 since it is grounded. From this information, the induced charge appearing becomes minus Q by 2. That means our final charge distribution becomes minus Q by 2 plus Q by 2 minus Q by 2 plus original charge Q. This is the final charge distribution on all the surfaces. Now, for drawing the graph, we should know the potential functions as well as electric field functions. Let's check out for the potential functions first. Since inner shell is grounded, potential inside it should be 0. That means from 0 to A, our graph should show 0 potential. Now check the region between the shells. In this region, at distance r from the inner shell, the potential becomes potential of the induced charge, which is this value, plus potential due to charge on the outer surface, which becomes this value. This is the potential in the region between the shells. When we consider outside region, for outside points, it should behave as a charge constant at its center. Now we can check the graphs. As we can see, the potential from 0 to A was 0. That means option B shows 0 potential from 0 to A, and from A to 2A, from to A, this is the potential function. This potential function from A to 2A. We can see that its value at R equal to 2A comes out to be plus KQ by 4A. That means potential varies from 0 to KQ by 4A. And beyond that point, when we come outside, it decreases as 1 by R. That means option B is correct. So this becomes the potential graph. Next we check the electric field graph. As we can see, in finite charge distribution, inside field should be 0. And between the shells, field should vary as 1 by R square. But direction of field is radially inward. And outside, direction of field is radially outward. That means between the region A to 2A, field is negative depending on 1 by R square function. And outside is positive depending on 1 by R square function. Therefore, the option C is the most appropriate answer. The final answer is B and C. Question number 15 is based on the fact that gravitational force is a central force, and under the influence of central forces, angular momentum is conserved. Secondly, we have been talked about Newton's first law. It says that what happens after gravity vanishes. When gravity vanishes at this point, external force becomes 0. The particle continues along a straight line. And once it continues along a straight line, the area swept by radius vector will be constant because all the triangles formed in this have same base length and same height. Means area swept are equal, which is actually Kepler's law, that area vector sweeps equal, radius vector sweeps equal areas in equal time intervals, which is actually Kepler's law. Now we can check the options. Option A says Newton's first law is obeyed on planet after gravity vanishes. It's true. B option, Kepler's law of area is obeyed only till the planet is in gravity of star. It is obeyed during this part as well as during the part when gravity vanishes. C, Kepler's law of area is obeyed even after gravity vanishes. It's true. D option, angular momentum of planet about center of star is conserved throughout its motion because gravitational force is always central force, always directed towards the source of the force. So angular momentum must be conserved. So finally, our answers are A, C and D.